All right. Good morning, everybody. Today we're going to talk about the process called utilizing sequences. Sequences, we have two types. We have arithmetic and we have geometric. With arithmetic sequences, the numbers like 1, 3, 5, 7, 9, where each number in the sequence follows some addition or subtraction process. So 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 2 is 7, and so on and so forth. So to determine the difference between those, we have 3 minus 1 equals 2. It's called a common difference. So between any two pair of numbers, sequential numbers, it has the same difference. So it's x2 minus x1. The geometric has what's called a common ratio. For example, like 1 times 3 is 3, times 3 is 9, times 3 is 27, and so on and so forth. So this is a geometric series because if we take these numbers and divide them, it's always the same ratio. So that's how we look at arithmetic and geometric sequences. The way we represent them is we use indices. What this one means here is, so n is the index. So here's my n, here's my index. It could be 1, 2, 3, 4, 5, 6. So for a sub 1, it's going to be square root of 1. A sub 2, it's going to be a square root of 2. A sub 3, it's a square root of 3 because n is these two are the same numbers, and so on and so forth. Another way we could look at them, it could be an equation. Usually ends are the same things as indices, starting from 1, or even you start at 0 if you want. It doesn't matter where you started off. As long as here we couldn't start off with 0 because of the denominator, so we have to start off with 1. So b sub 1 is negative 1. 1 plus 1 is 2. 1 over 1. So that's 1 times 1 is 1. Now when n is 2, it's negative 1. 2 plus 1 is 3. 1 over 2. Negative 1 cubed is negative 1. Times 1/2 is negative 1/2. The third one, b sub 3. Negative 1, 3 plus 1 is 4. 1 over 3. Negative 1 to the fourth is positive 1. 1/3, so it's 1/3. So it's, and then at b sub 4, it's negative 1. 4 plus 1 is 5. 1 over 5. Negative 1 to the fifth is negative 1. 1 over 5, so it's negative 1 over 5. So as the index gets larger, what we notice in this one, the values are getting smaller, but it's positive, negative, positive, negative. They oscillate. They oscillate, but they converge. Eventually, as we go to infinity, this thing will go down to zero. Another one. Again, because it's a rational, it ends on the bottom, n cannot be zero. So we start off with one. So C1 is 1 minus 1 over 1 is 0. C2 is 2 minus 1 over 2 is 1/2. C3, 3 minus 1 is 2/3. C4 is 4 minus 1 over 4th is 3/4. So we see it's slowly getting larger. So that one's going to converge. It's going to start off at 0 and then get bigger. No, get bigger. It's always going to be positive. This one, so when n is 1, so D1 is -1, 1 plus 1 is 2. -1 squared is 1. D2, -1, 2 plus 1 is 3. -1 cubed is -1. So D3, it's -1, 3 plus 1 is 4. -1 to the 4th is +1. And we see a pattern here. It's going to oscillate between +1 and -1. So we have -1, 4 plus 1 is 5. -1 to the 5th is -1. So it always goes positive, negative, positive, -1. All right, so that's what we're looking at as sequences. Convergence and divergence of sequences. So for example, if we had 1 over n is our function. Again, we look at our indices 1, 2, 3, 4, 5, 6. We're going towards infinity. When n is 1, we have 1 over 1, that's 1. 1 over 2 is 1/2, 1 over 3, 1 over 4, 1 over 5, 1 over 6. So what's happening here, as the n's get larger, these values get smaller. Eventually, it goes down to 0, so it converges. Converges to a finite number. All right. So how about now another one? How about this one? 1 minus 1 over n. Same thing as n goes. So we have 1 minus 1 over 1, which is 1 minus 1 is 0. 1 minus 1/2 is 1/2. 1 minus 1/3 is 2/3. 1 minus 1/4 is 3/4. 1 minus 1/5 is 4/5. And it keeps on going. So what's happening here is as these fractions, as the number gets larger, this number goes to 0. So we converge to 1. And looking at the graphs of these, so let's look at the definition. The definition of convergent. We say the sequence A, this is what defines, that's how we represent the sequence. The sequence converges to the number L if for every positive number epsilon, that corresponds an integer n such that the absolute value of a sub n minus L is less than epsilon when n is greater, little n is greater than larger n. And we did this from the limit theorem. So as a sub n, the value of the sequence approaches the limit, it's smaller than some epsilon whenever n goes to infinity, it gets large. It's divergent if no such number L exists. So it converges to a number L. So if it approaches and reaches a finite value L, then it converges. If it doesn't, it goes to infinity. If it doesn't go to some value, it goes to there. So again, we look at this. This is the limit. So we say this. The limit as n approaches infinity of our sequence equals L, or we can write a sub n approaches L. We call that the limit. So exactly, so we do it as we did earlier. All right, so let's look at the first example. Let's look at the limit as n approaches infinity of 1 over n equals 0. The limit as n approaches infinity of k, some constant, is k. Any constant k. So let's look at this. So according to our definition, is for any positive number epsilon. So epsilon has to be greater than 0. We need to show that an integer n exists. Doing here. There has to be a corresponding integer such that this is true. Such that a sub n minus L is less than epsilon. When n is greater than capital N. All right, so this is our A, so we have 1 over n minus the limit. This is our limit, so we have the limit of A sub n equals L. So it's minus 0 is less than some epsilon. So that equals absolute value of 1 over n. So we have 1 over n is less than epsilon. When n is greater than some capital N. So, I mean, n could be any number. So let's define it as 1 over little n. So is n larger than 1 over n? Yes. So now we got to show the limit as n goes to infinity of 1 over n equals 0. Because as n gets larger, this number gets smaller, eventually goes to 0. So the limit as n approaches infinity of some constant is k. Again, where epsilon has to be greater than 0. We need to show that these are the conditions that we have to show. So looking at this, we have our A sub n is k, our limit is k. So that's got to be less than some epsilon. K minus k is 0. And so that's always true. But remember, epsilon has to be greater than 0. So if it's greater than 0, it's obviously greater than 0. So the limit as n goes to infinity of a constant function is that constant function. All right. Let's look at example 2. Get this out of here. Example 2. Show there's a squiggly line, so it means this is a sequence. 1, -1, 1, -1, 1, -1, ... -1, n plus 1. Show that this sequence diverges. We can look at oh, okay, let me see. We have to prove A sub n minus L is less than some epsilon. So we have the limit of -1 n plus 1 as n goes to infinity equals some limit. If it exists, it equals some limit. But less than epsilon. So this thing can be +1 or -1. Where +1 minus 1 is 0. +1 plus 1 is 2. -1 minus 1 is -2. -1 plus 1 is 0. So this has, so if epsilon equals 0.02, these are obviously much larger than it. Since no single L exists, the sequence diverges. Call it oscillatory function because it alternates between positive, negative, positive, negative, positive, negative. The same values, +1, +1. Let's look at this. The sequence of radical n. As n goes to infinity, because of the graph, this one goes to infinity. It keeps on going up as x goes up, goes out. So it diverges. Because there's no single L value that it approaches. This is what we're looking at. The sequence A sub n diverges to infinity if for every number m there is an integer n such that for all n larger than n, then A sub n is larger than m. So the sequence S diverges to infinity if for every number m, there is an integer n such that for all n greater than m, A sub n is bigger than m. What this shows is the limit as n goes to infinity of our function, or we can write this is infinity. A sub n goes to infinity. It diverges. in order to converge, it has to reach an individual integer. Or I should say, it can be positive or negative infinity. Because if we look at the 1 over x, the function 1 over x, the limit as x approaches 0 from the left, this one goes to negative infinity. As the limit approaches 0 from the right, it goes to positive infinity. So let's look at when can a sequence diverge? So far, if the sequence goes to infinity, or if the sequence oscillates, or it's going between two numbers, say plus or minus 1. Calculating the limits of sequences. So here we're looking at that interval. So according to theorem 1, let A sub n and B sub n be sequences of real numbers. And let A and B be real numbers. We'll call these the rules of sequences. Then the following hold. The limit as n goes to infinity of A sub n plus B sub n equals A plus B. That's a sum rule. The limit as n goes to infinity of A sub n minus B sub n equals A minus B, called the difference rule. The limit as n approaches infinity of some constant times A sub n is the constant multiple rule. Then if we have the limit as n approaches infinity of a sub n times b sub n, then we have a times b, the product rule. And lastly, we have the limit as n approaches infinity of a sub n over b sub n equals a over b. This is the quotient rule. Of course, where b cannot equal 0. Again, we have these same rules pretty much for limits, for derivatives, everything else. So it's just applying them specifically what we're doing here. We have the product, the quotient, the constant multiple, the constant, the sum, the difference. It's just always the same ones. Example 3. Using theorem 1, limit as n approaches infinity of -1 over n. So we know this is a constant multiple, so it can go out in front. It's actually -1, but as n goes to infinity of 1 over n, as n goes to infinity, this value goes to 0. So the answer is 0. B. The limit as n approaches infinity of n minus 1 over n. All right, so since we have a monomial on the bottom, we could separate those and then use a difference rule. So we have n over n minus 1 over n. So it's a limit as n approaches infinity of 1 minus 1 over n. It's a difference rule, so I could split those. The limit of n goes to infinity of 1 minus the limit of 1 over n as n goes to infinity. The limit of a constant is the constant. Limit of 1 over n goes to 0. So the answer is 1. C. The limit as n approaches infinity of 5 over n squared. We have constant multiple on top, so it can go out in front. N goes to infinity of 1 over n squared. Here we can use the product rule, because this one is made up of limit n 1 over n times 1 over n. So we have the limit of n approaches infinity of 1 over n times the limit as n approaches infinity of 1 over n. These both go to 0. So the answer is 0. The limit as n approaches infinity, 4 minus 7 n to the 6, n to the 6 plus 3. Okay. What we did in chapter 2 in Cal 1, when we take the limit, what we can do with this function is we could divide each term by the largest exponent to simplify it. Because if we go to infinity, that one top is going to infinity, bottom one's going to infinity. Actually, or we can also take L'Hopital's rule and see how that works out. All right, so, well, let's do it both ways. So if I take n to the 6th power and divide each one of them. So I have 4 over n to the 6th, 7 n to the 6th, n to the 6th, n to the 6th over n to the 6th, n to the 6th. Simplifying that, we got 4 over n to the 6th minus 7, 1 plus 3 n over 6. Now, as n goes to infinity, this one goes to 0, this one goes to 0. So we have negative 7 over 1, which is negative 7. Look at the same one. This time, as n goes to infinity, we have 4 minus 7 n to the 6th, n to the 6 plus 3. If we just plug them in there, we get infinity over infinity, which means we can use L'Hopital's rule. Which means we take the derivative of the top and the derivative of the bottom. So that one goes to 0. So we have 7 times 6n to the 5th. That one goes to 0. So we have 6n to the 5th. Six n to the 5th cancel. So we have negative 7. Again, either way, you can use those however you want to. There's a note here. One consequence of theorem 1 is that every non-zero multiple of a divergent sequence diverges. Every non-zero multiple of a divergent sequence A sub n diverges. All right, so this defines the constant multiple rule, where if we had the limit of n goes to infinity of k a sub n, if a sub n diverges, I mean, goes to infinity, then so does that constant multiple of that function. It, the same goes for converging. If you have a non-zero multiple of a convergent sequence, then it converges. Works for convergent sequences also. So if it's a converging sequence as zero non-multiple, then if you multiply it, it's also going to be a convergent sequence. Theorem 2. The sandwich theorem. For sequences. Remember the earlier sandwich theorem we use is if we could find a function less than equal to less than equal to. So if we're looking for this equation there, and we can find two functions that are on both sides that are either convergent, in this case, it'd be either convergent or divergent. Earlier in chapter 2, we learned about sine x over x. We compared it to 1 is less than sine x over x, which is less than cosine x over x. So since both of the n values go to 1, the middle one has to go to 1. And we'll do the same thing with the sequences. If the f of x and g of x both approach the same value, then the middle one has to be also to that same value. Here's what it says. Let the sequence an and sequence bn and the sequence cn would be sequences of real numbers. If a sub n is less than equal to b sub n is less than equal to c sub n, holds for all n beyond some index n. So if that's true, you have first sequence is less than sequence less than third. And if the limit as n approaches infinity of a sub n equals the limit as n approaches infinity of c sub n equals the same value, then the limit of the middle one as n goes to infinity of b sub n also has to approach that same value. That's the limit there, the squeeze theorem, which we used. Again, we use that to prove sine x over x is equal to 1. All right. Example 4. Since 1 over n approaches 0, we know the following. Cosine n over n approaches 0. We know 1 over 2 to the power n goes to 0. we know -1 to the power n, 1 over n goes to 0. And that if the sequence a sub n goes to 0, then the limit goes to 0. Here's the reason. The reasons. The same thing we did with the sandwich theorem for the sine function. Cosine over n over n. Cosine is bounded by -1 and 1. So if we know, if we have an n on the bottom, because -1 over n as n goes to infinity goes to 0, that one goes to 0, so that one goes to 0. All right. What do we know about 1 over 2 to the power n? We have to pick two values. It's got to be bigger than 0, and it's got to be less than 1 over n. So that's 0. As n goes to infinity, that goes to 0. So this one has to go to 0. So this is the same as the cosine one. So you have the 1 over n. So it has to be less than positive 1 over n or greater than, or and greater than -1 over n. So as n goes to infinity, this one goes to 0, that one goes to 0. So squeeze theorem tells us that one goes to 0. No, so this is the absolute value. Is if the absolute value of a goes to 0, absolute value is the negative and the positive. So if both of these go to 0, if that's true, it means the positive and the negative goes to 0. That means that one has to go to 0. Pretty much common sense now once you look at that. Theorem 3. The continuous function theorem for sequences. Let the sequence a sub n be a sequence of real numbers if a sub n approaches some limit value, and if f is a function that is continuous at the limit value L, and also it's defined at all of the values of the sequence, then the function of the sequence is equal to the function, or goes to the function of the limit. Basically saying, if this is true, then we use these as inputs with the same values. But it's got to be a continuous function at all points. Think about that. If it's a continuous function, that means it has to be on a closed interval AB. And then there has to be a C value such that f of C is equal to the limit. Since C is inside A and B, that means it's continuous at the limit value. Since it's defined at all these points, then the function of the sequence values has to eventually lead towards the limit values. Example 5. Show the radical of n plus 1 over n approaches 1. All right. What do we know about the inside? As n goes to infinity, we have the limit of n over n plus 1 over n. So it's the limit as n approaches infinity of 1 plus 1 over n. This one goes to 0, so it equals to 1. So since that's the limit of the inside, then the square root is of 1 is 1. Example 6. The sequence 1 over n converges to 0. By taking a sub n equals 1 over n, f of x is equal to 2x. L equals 0. So theorem 3, so if this is my input, this is my function, and my limit. So 1 over L goes to 0. So we know that a sub n goes to L. So that's what this says so far. Show the sequence 2 to the power 1 over n converges to 1. So we know, here's the solution. Because we know the limit as n approaches infinity of a sub n, which is the limit as n approaches infinity of 1 over n approaches 0, then from theorem 3, so this becomes a sub 0, a to 0, and the function of x is 2 to the 0, 2 to the 0 is 1. So 2 to the n, or 1 over n, approaches sequence, approaches 1. And we've done this already. Use L'Hopital's rule. Suppose the function f of x is defined for all x's greater than or equal to n sub 0. And that the sequence a sub n is a sequence of real numbers such that a sub n equals f of n for n larger than or equal. So suppose that we have this function. It's a sequence. Then the limit of the sequence as n goes to infinity equals L when the limit of the function as x goes to infinity goes to same value L. Show the limit as n approaches infinity of ln n over n goes to 0. L'Hopital's rule said first, ln of infinity over infinity equals infinity over infinity. So if it's infinity over infinity, so use L'Hopital's rule. L'Hopital's rule simply says take the derivative of the top, which makes it 1 over x. Take the derivative of the bottom, just 1 over n. You get 1. So equals 1 over n. So the limit as n approaches infinity of 1 over n over 1. As n goes to infinity, this one goes to 0. So the answer is the limited value is 0. It just does it a lot faster for us. Example 8. Does a sub n, n plus 1, n minus 1 to the power n converge? If so, find the limit of a sub n. All right. So if we look at the limit of this, so the limit as n goes to infinity of this function, we get infinity over infinity, so we can use L'Hopital's rule. To get rid of this, we have a sub n equals n plus 1 and minus 1 to the power n. We can't do L'Hopital's as long as we have an exponent. So take the ln of both sides. So that means the exponent comes out in front. Now we take a look at these. Take the limits as n goes to infinity of a sub n. The limit as n goes to infinity of n ln n plus 1 n minus 1. So as n goes to infinity, we get infinity this goes to 1, so it goes 0. So we can use L'Hopital's rule here because we're going to that. So we can rewrite this as, in order to use L'Hopital's rule, we have to have a fraction. So our top number is going to be, and this number is, so we reciprocate it. So this goes to ln of 1, which is 0, and this goes to 0 as n goes to infinity. So we have 0 over 0. So now I take the derivative of the top. The derivative of the top will become 1 over times the derivative of the inside. It's just 1. Bottom becomes the derivative. So we get -2 or -1 n to the power -2. So the bottom number is -1 over n squared. So the ln is this. Now we take the derivative of the inside. So the numerator, the denominator, the derivative. So that becomes n minus 1 minus n plus 1 over n minus 1 squared. So n minus 1 minus n minus 1, n minus 1 squared. So it's -2 over n minus 1 squared. Yeah, so the limit n approaches infinity Yeah, so it's 1 over that times this. -2 over n minus 1 squared. So we have -2n minus 1 squared times the flip of the bottom, n minus 1 and plus 1. Those cancel. -2 over n minus 1 and plus 1 over -1 n squared. The limit as n approaches infinity n plus 1 and minus 1 So on the top, we have difference of two squareds. As n goes to infinity, you get 0 over 0. Yeah, let's see what we can fix here. So we have -2 n squared minus 1 times -n squared over 1. Take the top, leave it alone, flip the bottom. So negative is positive 2n squared over n squared minus 1. Divide everybody by n squared. So I have 2n squared over n squared, n squared over n squared, 1 over n squared, 2, 1 minus 1 over n squared. That one goes to 0, so you get 2. All that for 2. So what does that tell us? We know that ln a sub n is now equal to 2, or leads to 2. And our function so ln a2 so okay, find ln the limit as x2. Commonly occurring limits. Theorem 5. following sequences converge. As follows. The limit as n approaches infinity of ln n over n. So we get infinity over infinity, so it's 1 over. Since we use L'Hopital's rule, we got 1 over n over 1. So the limit as n goes to infinity is 0. The limit as n goes to infinity of the nth root of n n goes to infinity of n to the power 1 over n. As n goes to infinity, so as n goes to infinity, so 1 over infinity, this goes to 0. So we have n to the 0, which is 1. The limit as n goes to infinity of x 1 over n for any value n, or for any value x greater than 0, for any positive x, because if not, we have an alternating series. So as this goes to 0, as n goes to infinity, so x to the 0 is 1. Four. The limit as n goes to infinity of x to the power n This is for any absolute value of x is less than 1. Yeah, okay, so if x is less than 1, that means it's a fraction. So what we're left with so this becomes some fraction, the limit of 1 over a. So that becomes 1 over a to the power n. As n goes to infinity, this one goes to 0. The limit as n goes to infinity, 1 plus x to the power n. This is a, in your cheat sheet, it'll just tell us that this becomes x. That's just straight from the cheat sheet. The limit as n approaches infinity for any x. So this is just a exponential one. This is a factorial, which means you multiply everything from n down to 1. So as n gets bigger, this one gets bigger, so it goes to 0. Yeah, because the bottom number gets a lot bigger, a lot faster than the top number does. Example 9. Using theorem 5, solve these. N squared over n. Using the rules of natural log or logarithms. And then using theorem 5, that goes to 0. So it's 2 times 0 equals 0. So that means, which is the same thing as 1 to the power n to the power 2. This one goes to 1. Squared is 1. Directly from the theorem. Cube root, or nth root of 3n. Which is 3 to the power 1n. N to the power 1n. As n goes to infinity, this goes to 0. That goes to 0. So we have 1 times 1 equals 1. Negative 1/2 to the power n. So as n gets larger, this goes, so it goes to 0. N minus 2 over n to the power n. This is n over n minus 2 to the power n. 1 minus 2n, which is 1 plus negative 2 to the power n. E to the power negative 2. It's e to the power x. And then the last one, 100 to the power n divided by n factorial. And is 0 because the bottom goes a lot faster. And what do we have? Ooh. All right. Recursive definitions. Sequences can often happen recursively, meaning that they repeat each other or repeat themselves, or some follow some sequence. Now here we have the definitions. We've calculated each a sub n sequence directly from the values of n, but sequences often defined recursively by giving the values of the initial terms or terms, and they follow some sequence, a rule called a recursion formula for calculating any later terms in that function. So let's look at example 10. These are recursively. So you get the first term as a is 1, then the formula for all the other ones, the recursive formula is this. So for a sub 2, we use a sub 1, which is 1, 1 plus 1 is 2. And then for a sub 3, then you use a sub 2 plus 1. And we get the sequences there. So a sub 2 is a sub 1 plus 1 is 2. A sub 3 is a sub 2, which is 2 plus 1 is 3, and so on. The statement a sub 1, a equals 1, a sub n, the recursive for it is this. So for a sub 2, we got 2 times a sub 1. So 2 times 1 is 2. That's that. A sub 3 is equal to 3 times a sub 2, which makes it 6. A sub 4 is 4 times a sub 3. So 4 times 6 is 24, which is, so that's what it says. That's it. And the rest of these, again, it all follows, it's an iterative recursive process where the previous function defines the next value. Initial term terms defined and recursive formula given. To find subsequent values. Now look at bounded monotonic sequences. And here's the definition. A sequence A sub n is bounded from above if there exists a number m such that all the sequence terms are less than m for all n, all the terms. M is an upper bound for the sequence. If M is an upper bound, for the sequence, but no number less than m is an upper bound, for the sequence, then m is the least upper bound. For the sequence. If m is an upper bound for a sub the sequence, but no number less than m is an upper bound, that means m is the least upper bound. If there is one that's less than m, then that becomes a new m. So that's the first part. That's the first part. The second part. No. a sequence A sub n is bounded from below if there exists a number little m such that A sub n is bigger than little m for all those values in the sequence. The number m is a lower bound for the sequence, if that exists. And like we said on the other side, if m is a lower bound for A sub n, but no number greater than m is a lower bound, for the sequence, then m is the greatest lower bound for the sequence. So if little m is a lower bound and there's no number larger than it that can be counted as lower bound, then m is the greatest lower bound. So if our sequence is bounded above and below, then the sequence is bounded. If it is not bounded, then it is unbounded. It is an unbounded sequence. Example 11. That's it. So A. The sequence 1, 2, 3, dot, 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 n, dot, dot, has no upper bound as it goes to infinity, which is greater than some value of m. The sequence is bounded below by every real number less than or equal to 1. So m equals 1, which is the greatest lower bound. The sequence 1/2, 2/3, 3/4, n plus 1 is bounded above by every real number equal to 1. So the upper bound m is equal to 1. It is the least upper bound. The sequence is bounded below by every real number, any number less than or equal to 1/2. The greatest lower bound. Yes, that's where it began. So with that, convergent sequences are bounded. Next example. So if it's convergent, that means it's bounded. Meaning it's bounded, it has an upper and lower bound. Now we're talking about non-increasing and non-decreasing, or let's define monotonics. So the definition. A sequence A sub n is non-decreasing if the let's say A sub 1 is less than A sub 2, is A sub 3 is less than A sub 4. In other words, A sub 1 is less than equal to A sub 2, which is less than equal to A sub 3, which is less than equal to A sub m, and so on and so forth. A sequence is non-increasing if A sub n is greater than A sub n plus one. For all. So all the subsequent ones are lower. So that's non-increasing, non-decreasing. A sequence is monotonic if it is either non-increasing or non-decreasing. In other words, there's no change. It's either goes up or it goes down. There's nothing else to look at. Which is defined in theorem 6. The monotonic sequence theorem. If a sequence A sub n is both bounded and monotonic, then the sequence converges. In other words, if it's bounded, means it has an upper and lower bound, it's bound in. And if it's monotonic, meaning it's either non-increasing or non-decreasing. If that's the case, if it's both of those, then it converges. All right, let's look at example 12, and that'll wrap up this section. The sequence 1, 2, 3 is non-decreasing. This is always increasing. The sequence 1/2, 2/3, 3/4, n plus 1 is non-decreasing. Because each of these values are getting larger and larger and larger. The sequence 1/2. No, that's so it's 1/2, 1/4, 1/8, ... 1/2 to the power n ... So you notice it's always getting smaller. So the function, the sequence is non-increasing. D. The sequence 3, 3, 3, dot, 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 3, dot, 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 is both non-increasing and non-decreasing. E. The sequence 1, -1, 1, -1, 1, -1 is not monotonic. Because it oscillates. All right. That does it for that section. All right. See you all next week.